ground rods have a limited surface area. This limits their ability to dissipate ground fault currents effectively. While using a larger conductor, for example a 1/0, may increase the ampacity of the conductor itself, it does not significantly improve the grounding effectiveness of a single ground rod. UFA grounds are highly effective. This is because they provide a large surface area in direct contact with the moist soil. This results in low resistance to ground. However, the effectiveness of a UFA ground can vary depending on the soil conditions and the size and depth of the concrete electrode. Even though a ground rod may not be an optimal grounding electrode, the National Electrical Code, specifically Table 250.166, requires a 1/0 copper grounding electrode conductor to be used with a single ground rod. This is intended to ensure a robust and reliable grounding path for a 300 ampere service. The 1/0 conductor is designed to handle the anticipated fault currents and prevent damage to the grounding system. Similarly, a 10-foot metal frame member in direct contact with the earth is also required to be connected with a 1/0 copper grounding electrode conductor. This is because the metal frame member may not provide a sufficiently low resistance to ground, especially under adverse conditions or in high resistivity soil. The 1/0 conductor helps to supplement the grounding capabilities of the metal frame and ensures a reliable ground path. Water pipes are often used as grounding electrodes. However, they can be unreliable due to factors such as corrosion, repairs, or replacement. The NEC requires that water pipes be supplemented with a separate grounding electrode to ensure a backup grounding path in case the water pipe becomes ineffective. The 1/0 copper grounding electrode conductor is intended to provide this backup grounding path. The requirement for a 1/0 copper grounding electrode conductor with specific electrodes such as ground rods, metal frame members, or water pipes is based on the need for a robust and reliable grounding system. While certain electrodes may provide better grounding capabilities, for example UFA grounds, the 1/0 conductor ensures a consistent level of grounding effectiveness across various electrode types and soil conditions. Now let's delve into the specifics of grounding electrode conductors and the reasons behind the NEC requirements. The primary purpose of a grounding electrode system is to provide a low impedance path for fault current to return to the source. This facilitates the operation of overcurrent protective devices like circuit breakers or fuses, quickly disconnecting the circuit and minimizing the risk of electrical shock or fire. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in NEC Table 250.166. This table ensures that the grounding electrode conductor is adequately sized to handle the potential fault current. Ground rods, despite their limitations and surface area, are commonly used as grounding electrodes due to their ease of installation. However, a single ground rod often has a higher resistance to ground compared to other electrodes like UFA grounds. The NEC requires a minimum of 2 ground rods to be installed and bonded together to lower the overall resistance. In cases where 2 ground rods are used, the grounding electrode conductor must still be sized according to Table 250.166, which often results in a 1/0 copper conductor for a 300 ampere service. This larger conductor size helps to compensate for the inherent limitations of ground rods. UFA grounds, or concrete encased electrodes, are considered highly effective because the concrete provides a large surface area in contact with the earth, and the moisture in the concrete helps to maintain a low resistance to ground. The NEC recognizes the effectiveness of UFA grounds and allows for a smaller grounding electrode conductor size, typically a number 4 American wire gauge copper conductor. However, the UFA ground must meet specific requirements, such as being encased in at least 2 inches of concrete and being located within the footing or foundation of the building. Metal frame members that are in direct contact with the earth or encased in concrete can also serve as grounding electrodes. However, their effectiveness depends on the size and depth of the metal frame, as well as the soil conditions. The NEC requires a 1/0 copper grounding electrode conductor for metal frame members to ensure a reliable grounding path, especially in situations where the metal frame may not provide a sufficiently low resistance to ground on its own. Water pipes are traditionally used as grounding electrodes, but their reliability has decreased over time due to the increasing use of non-conductive materials in water systems, such as PVC pipes. Additionally, water pipes are susceptible to corrosion and may be disconnected during repairs or replacements. For these reasons, the NEC requires that water pipes be supplemented with another type of grounding electrode, such as a ground rod or a U for ground. The grounding electrode conductor for the water pipe must be sized according to Table 250.166, and the supplemental electrode must also be connected to the grounding system. The 1/0 copper conductor requirement for water pipes helps to ensure a reliable grounding path, even if the water pipe becomes ineffective. The choice of grounding electrode and the size of the grounding electrode conductor should be based on a thorough assessment of the site conditions, including soil resistivity, the availability of suitable electrodes, and the requirements of the NEC. A qualified electrical engineer or electrician should be consulted to ensure that the grounding system is properly designed and installed. In summary, the seemingly oversized grounding electrode conductor requirements for certain electrodes, such as ground rods and metal frame members, are intended to compensate for their inherent limitations and to ensure a robust and reliable grounding system that can effectively handle fault currents and protect against electrical hazards. The NEC prioritizes safety and reliability, and the grounding electrode conductor size requirements are a critical aspect of achieving these goals. Now let's consider some additional factors that influence the selection and sizing of grounding electrode conductors. Soil resistivity is a crucial factor in determining the effectiveness of a grounding electrode. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity indicates that the soil is a good conductor, while high soil resistivity indicates that the soil is a poor conductor. In areas with high soil resistivity, it may be necessary to use multiple ground rods or other grounding electrodes to achieve a sufficiently low resistance to ground. The NEC does not specify a maximum resistance to ground for grounding electrodes, but it is generally recommended to achieve a resistance of 25 ohms or less. This can be measured using a ground resistance tester. The length and diameter of ground rods also affect their effectiveness. Longer ground rods have a larger surface area in contact with the soil, which helps to lower the resistance to ground. Similarly, ground rods with a larger diameter also have a larger surface area. The NEC requires ground rods to be at least 8 feet long and have a minimum diameter of 5/8 inch. The material of the grounding electrode conductor is also important. Copper is the most common material used for grounding electrode conductors due to its excellent conductivity and corrosion resistance. However, aluminum conductors are also permitted under certain conditions, but they must be sized larger than copper conductors to provide equivalent conductivity. The grounding electrode conductor must be properly connected to the grounding electrode using approved methods such as exothermic welding or listed connectors. These connections must be corrosion resistant and able to withstand the mechanical stresses of the installation. The grounding electrode conductor must also be protected from physical damage. This can be achieved by installing the conductor in conduit or by using a heavy-duty cable. The routing of the grounding electrode conductor is also important. The conductor should be run in a direct path from the service equipment to the grounding electrode, avoiding sharp bends or unnecessary loops. The length of the grounding electrode conductor should also be minimized to reduce impedance. The NEC provides specific requirements for the installation of grounding electrode conductors in different types of buildings and structures. These requirements may vary depending on the occupancy, the type of electrical system, and the presence of other grounding electrodes. In some cases, it may be necessary to install a grounding electrode system that includes multiple types of electrodes, such as a ground rod, a U for ground, and a metal frame member. This can help to ensure a robust and reliable grounding system that meets the specific needs of the installation. The grounding electrode system should be inspected and tested regularly to ensure that it is functioning properly. This should include visual inspections of the grounding electrodes and conductors, as well as ground resistance testing. Any damage or corrosion should be repaired promptly. The grounding electrode system is a critical component of the electrical system, and it should be treated with the same care and attention as other important electrical equipment. A properly designed and installed grounding electrode system can help to protect against electrical shock, fire, and equipment damage. It is essential to consult with a qualified electrical engineer or electrician to ensure that the grounding electrode system meets the requirements of the NEC and the specific needs of the installation. Remember that electrical codes and regulations are subject to change, so it's always important to refer to the latest edition of the NEC and any applicable local codes. Grounding is a complex topic, and it's important to have a thorough understanding of the principles involved to ensure a safe and reliable electrical system. Always prioritize safety when working with electricity and seek professional assistance when needed. The information provided here is intended for educational purposes only and should not be considered a substitute for professional advice. Now let's address some common misconceptions about grounding electrode conductors. One common misconception is that the grounding electrode conductor is only used to carry fault current during a ground fault. While this is one of its primary functions, the grounding electrode conductor also plays a role in stabilizing the voltage to ground and reducing electrical noise. Another misconception is that a larger grounding electrode conductor is always better. While it's important to size the grounding electrode conductor according to the NEC requirements, using a conductor that is significantly larger than required may not provide any additional benefit and can increase the cost of the installation. A third misconception is that the single ground rod is sufficient for all grounding applications. As discussed earlier, a single ground rod often has a high resistance to ground, and the NEC requires a minimum of 2 ground rods to be installed and bonded together. A fourth misconception is that a UFA ground is always the best grounding electrode. While UFA grounds are generally very effective, their performance can vary depending on the soil conditions and the quality of the concrete. In some cases, other types of grounding electrodes may be more suitable. A fifth misconception is that the grounding electrode conductor is only necessary for the service entrance. While the service entrance is the most critical location for a grounding electrode conductor, grounding electrodes may also be required at other locations in the electrical system, such as separately derived systems and remote buildings. It's important to understand the specific requirements of the NEC and any applicable local codes to ensure that the grounding system is properly designed and installed throughout the entire electrical system. Grounding is not a one-size-fits-all solution, and the best approach will depend on the specific characteristics of the installation. Now, let's consider the impact of different types of soil on grounding electrode performance. Sandy soil typically has a high resistivity, which means it is a poor conductor of electricity. This is because sandy soil has large particles and poor water retention, resulting in fewer conductive pathways. In sandy soil, it may be necessary to use longer ground rods or multiple ground rods to achieve a sufficiently low resistance to ground. Clay soil typically has a lower resistivity than sandy soil, which means it is a better conductor of electricity. This is because clay soil has smaller particles and better water retention, resulting in more conductive pathways. However, clay soil can also be corrosive, which can damage grounding electrodes over time. Loamy soil is a mixture of sand, silt, and clay, and it typically has a moderate resistivity. Loamy soil is generally a good medium for grounding electrodes, as it provides a balance of conductivity and drainage. Rocky soil can be challenging for grounding electrode installation, as it may be difficult to drive ground rods into the ground. In rocky soil, it may be necessary to use alternative grounding methods, such as ground plates or concrete-encased electrodes. The moisture content of the soil also affects its resistivity. Moist soil is a better conductor of electricity than dry soil. This is because the water in the soil helps to create conductive pathways. In dry climates, it may be necessary to use methods to keep the soil around the grounding electrodes moist, such as installing a watering system or using a chemical ground rod. The temperature of the soil also affects its resistivity. Cold soil is a poorer conductor of electricity than warm soil. This is because the water in the soil can freeze, which reduces its conductivity. In cold climates, it may be necessary to bury grounding electrodes deeper in the ground to avoid the effects of freezing. The presence of chemicals in the soil can also affect grounding electrode performance. Some chemicals can increase the conductivity of the soil, while others can decrease it. Corrosive chemicals can also damage grounding electrodes over time. It's important to consider the soil conditions when selecting and installing grounding electrodes. A soil resistivity test can be performed to determine the resistivity of the soil at a particular location. This information can be used to select the appropriate type and size of grounding electrodes and to determine the optimal spacing between multiple electrodes. Now let's discuss the importance of bonding in grounding systems. Bonding is the process of connecting together all metal parts of the electrical system, as well as any metal parts that are likely to become energized. This includes metal conduits, metal enclosures, metal water pipes, and metal building frames. The purpose of bonding is to create a low impedance path for fault current to flow back to the source. This helps to ensure that overcurrent protective devices will operate quickly and effectively, minimizing the risk of electrical shock or fire. The bonding conductors must be sized according to the NEC requirements, which are based on the size of the overcurrent protective devices in the circuit. The bonding conductors must be securely connected to the metal parts using approved methods such as bonding jumpers or bonding lock nuts. The bonding connections must be corrosion resistant and able to withstand the mechanical stresses of the installation. The bonding conductors must be protected from physical damage. This can be achieved by installing the conductors in conduit or by using a heavy-duty cable. The bonding system should be inspected and tested regularly to ensure that it is functioning properly. This should include visual inspections of the bonding conductors and connections, as well as continuity testing. Any damage or corrosion should be repaired promptly. Bonding is a critical component of a safe and effective grounding system. A properly bonded system helps to minimize the risk of electrical shock and fire, and it helps to ensure that electrical equipment will operate properly. It's important to understand the principles of bonding and to follow the NEC requirements when installing and maintaining bonding systems. Now let's briefly touch on surge protection and its relationship to grounding. Surge protective devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning, utility switching, or other events. SPD work by diverting surge current to ground, thereby limiting the voltage that reaches the protected equipment. A properly designed and installed grounding system is essential for the effective operation of SPD. The grounding system provides a low impedance path for the surge current to flow to ground, which helps to minimize the voltage rise and protect the equipment. The SPD should be connected to the grounding system using a short, direct conductor. The length of the conductor should be minimized to reduce impedance. The SPD should be located as close as possible to the equipment being protected. The grounding system should be inspected and tested regularly to ensure that it is functioning properly. This is especially important after a lightning strike or other surge event. Surge protection is an important aspect of electrical safety, and it should be considered in conjunction with grounding when designing and installing electrical systems. Now, consider that we are discussing general practices and requirements. It is always important to consult the latest edition of the NEC and any applicable local codes. The NEC is a comprehensive document that provides detailed requirements for electrical installations, and it is essential to follow these requirements to ensure a safe and reliable electrical system. Local codes may also have additional requirements that must be followed. It's important to work with a qualified electrical engineer or electrician who is familiar with the NEC and local codes to ensure that the electrical system is properly designed and installed. Electrical work can be dangerous, and it should only be performed by qualified individuals. Always prioritize safety when working with electricity and seek professional assistance when needed.